السلام عليكم. أنا اسمي حامد الرويشيدي من برونيل يونيفرسيتي. الموضوع مالتي اليوم هو 6G. يعني راح أعطيكم فد نبذة مختصرة عن ال 6G. Okay, I'm going to talk about what is 6G, Iris, Open RAN, 6G with the quantum communication, and I will show you current and the future research at WNCG. Okay, just before I will talk about the 6G, I would like to give you some introduction about why we need 6G. Yani all of us, maybe some of you have been witnessing first generation, second generation, and then third generation. Some people, they say in Iraq there is fourth generation, which is, I doubt it. There is LTE, but there is no LTEA. And there is 5G, which is in Europe, maybe in the Gulf country, America, Japan, China, all of them, they use 5G. And hopefully within the next 6 years, in 2028, 2030, we're going to see 6G, okay? Now, one of the reasons why we have first generation, second, third, and fourth, right, let us see here, in 2000, okay, in 2000, if you look to the 2000, we have only 1,000 applications. After about 11 years, the application increased to 350,000. In 2020, I think this is Bilal's slide. I took it from him, yes? I don't know. Anyway, in 2020, we have more than billions of applications, which means that if you spend all your time to see all the application, it is very difficult to see all the application. This is another reason why we need 6G. If you look at the amount of data we have in, say, 2019, 13.5, while in 2025 we will have even more than 80. This is something in zettabyte, which means you have a huge amount of information. I give you example. Data, when you transfer data, it's look like when you have so many people and you want to transfer them, and or you want to travel them from one point, say from Baghdad to any country. So you need a huge number of buses or taxis or whatever. So we need to deal with those data in a way. And if you look here, this is the number of connected devices. Okay, and if you see in 2019 we have 7.74, while in 2030 we might have even more than 30 billions devices. So everything in the next future, all of you have this mobile, you will be able to control everything from the mobile. So we need something new. Plus the application will be different in the next future. We will have something, the application we will have is totally different. Sometime we're going to have a car which is called autonomous vehicle, which means this car without driver. Now the delay here in this case is very important. Somebody, say, sitting in one of the hospital here and want to do an operation, okay, to somebody in Japan, then the delay is very important. So this will depend on so many issues. Just to give you an idea, because this is very important for you to understand. I'm not going to go through all this, but let me go through the data rate and the frequency and the bandwidth. As you have a huge bandwidth, you will be able to transmit a huge amount of data. as you are working on a higher frequency, you will be able to transmit a huge amount of data. So if you look to the first generation, and this is in 1980, which is most of you haven't been witness this first generation. Those are the frequency. It was analog, now we have digital. And if you look to the second generation, again, most of you haven't seen this. Okay, third generation, maybe some of you or not. If you look to the bandwidth, still 25 megahertz, and then in 2009 we have 4G 100 megahertz, and now we are working on, which is the fifth generation, on 100 megahertz, and this is in 6G we have something above 400 megahertz. This is just the bandwidth, okay? And this means that as we increase, as we said, as we increase the bandwidth, it means we're going to increase the amount of data. Now, if we come to the frequency, this is where everything will be changed with the frequency. When you work with the low frequency, then simple problem. When you increase the frequency, you will get a lot of problems, and I will explain why. Then when you go to the third generation, you're going to have higher frequency to be able to put a huge amount of data. Now with the fourth generation, we have higher frequency. With the fifth generation, we work on something called millimeter wave, which is between 24 to 86 to even 100 gigahertz, and this is called a higher frequency. And I will tell you why the higher frequency has a certain advantage and disadvantage. Look to the sixth generation, which is, I'm going to talk about it. It's something till 400 gigahertz. Now all my students now, none of them working on fifth generation. All my students working on what we call a sixth generation, which is between 200 and 400 gigahertz. Now what's the problem with this kind of, they call it terahertz. This one they call it millihertz, millimeter wave. This one they call it terahertz. Anything above 100 gigahertz, which is 0.1 terahertz till 3 terahertz, this is called terahertz. Now with the terahertz, when you transmit the signal in this frequency, you could transmit the signal for a few kilometers. So if you have your mobile and you want to communicate with the base station, then if it is even 5-6 kilometers, there will be no problem. The problem, when you increase the frequency, the attenuation will be huge. I could, with this frequency, I will be able to transmit maybe 100 meters, even less than this, and it should be line of sight. The meaning of line of sight, I'm going to transmit a signal from myself, say from this position to any one of you. But if I will transmit a signal to somebody outside this room, there will be a big problem. No way they will be able to receive it. I need to find a way, okay, to be able to let somebody outside this room to receive the signal. And what is the, how I will be able to open, to try to transmit the signal if somebody outside the room. Either I will open the door and put a mirror or something related similar to the mirror, and then I transmit the signal. And I am going to talk about this later as well. So one of the problem of this terahertz or this frequency is that huge attenuation, and there is only communication between line of sight. Now if somebody now will have a mobile, as I said, and he is outside this room, he will not be able to communicate, but we need him or her to communicate. What we're going to do, we're going to find a way for communication, and I will explain it later on. Now this is the beauty. If you look to the data rate, look to the data rate here. this is up between 2.4 to 14.4, and then 14.4, 3100 meg, and then up to 20 gigabit per second. With the 6G, you will be able to transmit 1 terabyte, which means 1,000. And this is the difference. There is no difference. All the basic is similar, but we need to find a technology to be able to transmit. As I said, as far as I know, Iraq has only 3G, because 4G, it means LTEA, which is long-term evolution advance. Iraq, I think they use only LTE, which means 3, either 0.5, 0.8, 0.9, but not 4th generation till now. One thing I want to explain it. In UK, there were a few operators. One of them hasn't got any kind of generation. And the three of them, they have 1st generation, 2nd generation, and 3rd generation. And they went to the 4th generation. The new operator started directly from 4th generation. So my advice, if you want to start something, you need to start from here. You don't need to you don't need to start from 4th generation, because all the country now using 5th generation. Right, let me just go and show you again what is the vision of the 6th generation. If you look, this is the 5th generation. Look to the capacity. The meaning of the capacity is how many users, okay, we will be able to have, okay. And I'm going to talk about some important issue, which is user data rate. And this is what I am interested in, latency. I'm interested in two things mainly. Power, of course, security is very important, but power is very important for me for two reasons. One thing is to generate power, it will cost you money. When you generate power, you will get CO2, and you're going to destroy the environment. And the other thing, if you spend a lot of power, you transmit a huge amount of data, okay? When we had the 1st generation, 2nd generation, all what you could do, either send SMS or you call your mom or dad, okay? Sometimes you call your colleagues as well. But when you have something now, what we have, we use video, we sometimes open a camera, we talk with somebody. In the future, you're going to get something else. Somebody cooking a nice food, Iraqi food, you could smell it in the future, okay? So latency, as I said, is very important, because there are a lot of applications in the future. Latency is very important. So this is the difference between 6th generation and 5th generation. The latency will be 10 times, okay, better. And this is the comparison between the data rate and all these latency, mobility, all these things, which is the difference between them. And I could tell you, within the next 20 years, I'm going to work on 7G. And within next 30 years, we're going to work on 8G. And this is, you know, anybody could not understand why we work on 5th generation, 6th generation, 7th generation for so many reasons. Now, somebody will say, as you know, I did my degree, I graduated from University of Technology here in Iraq in 2000. Yes? Are you with me or not? 2000. Yeah. Okay, so I will be able to do some research maybe in the 8th generation. which is, I'm sure some of you, inshallah, will be able to do it and to try to do something. Now, I will go a bit technical about the kind of multiple access, okay? In 5th generation, we use something called OMA. And OMA means orthogonal multiple access, which means I'm going to allocate for each user a certain bandwidth, and give it to those people. And I will be able to transmit the signal. This is called orthogonal multiple access. In the 3rd generation, I'm going to give each one of you a certain code. Now, how I distinguish between people? Every student now, or every member of staff has a specific name, and I'm going to distinguish between them. In the 3rd generation, I give code for each one. But as you know, we don't have millions of code. Similar thing here, we don't have a huge bandwidth. One thing about bandwidth, there are two things. Bandwidth is called national security, which means in UK, if you put your car somewhere, somebody will come and steal it, and then you go to the police and then you report it, and nobody will do anything. But if somebody will transmit, like me, any information without having a license, believe me, 2 minutes, the meaning of NOMA, yes? NOMA. This is in Arabic, and in English means non-orthogonal multiple access, which means I'm going to give all of you same bandwidth, but giving them different power. The nearest to me, I will send him or her the lowest power. Further, I will send her or him a higher power. I don't want to go into details. This is how we have the release, where if you are a student, go to a website and put 3GPP, and you will be able to see all the information about release 18, 19, 20, and so on. I'm coming to something why we chosen this frequency. This is the frequency which is called a terahertz. Okay, we have radio waves, we have microwave, and then we have a terahertz. And this terahertz, as I said, it starts from 100 gigahertz, which is 0.1, till 10 terahertz. Okay, and this is what we call it a high frequency. Why we chosen 200 to 400? Why not 500 to 10 to 600? Because if you look here, the attenuation is the lowest in this frequency. This is the lowest in this frequency. And this is why we are interested in this frequency. Let me come to something else called MIMO, which is multiple input, multiple output. What is the meaning of multiple input, multiple output? In the old days, you have only one antenna here in the transmitter and one antenna in the receiver. Now, and then after that, they have multiple 2x2, maybe 4x4, all this called MIMO. And then after that, we used to have a massive MIMO, which means we could have 16x16 antenna. Now, when we came, this is all in 4G and 5G and 3G. But when we came to 6G, we have something called ultra massive MIMO, which means you will be able to have 100 antennas, okay, in your mobile. And this is here, 1 pence, this is 1 pence. Those people in my age, they know there used to be something called 50 فلس أو 25 فلس. This is the size, and with this size you will be able to have 100 antennas. The reason behind this, because if you put here antennas and you put your hand like this antenna will be blocked. As we said, this is a high frequency. When you put anything, this is another example, a third example where you will be able to have several scenarios, and this is the risk controller, where either you will be able to transmit the signal or reflect the signal in different angles. Now, I finish from the RIS or the iris, and I'm coming to something called Open RAN. And the Open RAN, it is something which is related to 6G. They starting now working on with 5G on Open RAN, but definitely they will use it in the 6G. And the meaning of Open RAN, it means that you will be able to buy anything from any operator or manufacturer and put it somewhere, and buy different things from another manufacturer and put it together. I could give you example. First generation, second generation, third generation. If you are in, say, Europe, you go to America, you need to change the SIM card to be able to work on third generation. This is a problem of the Open RAN, is that you have Open RAN, and then you have distributed, open distributed unit, central unit, and the rest is core unit. But you need to understand that in this case, we are using NOMA, which means non-orthogonal multiple access. This is the second thing we are starting working on it. Now, I could tell you, when I say we're working on 6G, it doesn't mean that everybody working on 6G. There are people still not working on 6G. When you have something new, and this is how you will be able to develop something or publish something, if you try to do research in something new rather than you work on something old. For example, if you work on control system, if you work on civil engineer, mechanics, something, it's not easy to publish or to develop something. In communication, you will be able to do everything, because I could tell you, if you publish something 2 years ago, or somebody published, after 2 years you can't do anything. And this is, everything is changing. Communication, things change very quickly. So you need to have a new idea. Now, the new idea here is that we have something called the quantum entanglement. And this is related to quantum computing, something related to physics as well. But there are something now very new, which is quantum communication. With the quantum communication and 6G, I haven't seen much publication worldwide, not anywhere, like in Europe, in America, in China, in Japan. There are, but very few. We started working on quantum communication with 6G. Now, the idea behind quantum communication, you have a laser beam, and then you split this laser beam to 2 beams, and you will be able to work here. Anything you do here, it will be changed there. Don't ask me how this is happening. I'm not expert in this, okay? Now, you could always have 1 beam here and 2 beam here, or 4 beam, or 8 or 16 or even 32, and you transmit each beam to different place. Now, when you do some changes here to the polarization, to the phase, everything will be changed there. 2 things you could get benefit from. Okay, Dr. Yusuf copying this, and they will be able to publish, and in fact you will be able to do everything, okay, on this, not only in communication. As I said, computing or anything else. Maybe I have one student now working on IoT with quantum communication. Okay, so right now, what is the benefit? Why we are bothered with quantum communication and something? As I said, 2 things: delay, very important, and power. So I'm going to reduce the power, reduce the cost. I will be able to have this mobile working because I could tell you in the next future, if you're going to transmit in terabyte, then this will be able, I don't know if you have seen this, when you put this on any application which take huge power, then after half an hour, if you use your location and you make it switch on all the time, after 1 hour maybe the power will be reduced more than 50%. So power is important. In addition to the power, the CO2, you're going to destroy it, and you need to pay a lot of money for power. Here, of course, in Iraq, power is so cheap, as we discuss it, and CO2 is not important. Delay is very important in a lot of application. Right, let me just go. Now everybody start become expert in quantum communication, yes? Okay, now this is what we have in, as I said, in distributed RAN, CRAN, VRAN, and Open RAN. This is what we are working on with the quantum communication. This is the first work which has been done using the Open RAN. If you look to this here, several radio unit and communicating with distributing unit and central unit, but we have done this using quantum entanglement. And this work has been published already, but this is all simulation. It is so expensive to build something in hardware, okay? And this is, now we are working on something similar to it again in Open RAN, and we try to modify this in the hopefully next few months, okay? Now, after all this, I gave you some introduction about quantum, Open RAN, maybe 6G, why we use 6G or 5G and 4G. I just want to show you what we do in my research center. In my research group, what we work on 6G and future IoT. And we have industrial IoT, we have what we call it intelligent IoT, cloudification, SDN, big data, all this far edge, near edge, and some application in the health as well, which is called digital twin. This is the CRAN, and we have published the first CRAN paper where we use certain kind. I don't know if this is your work, Dr. Yusuf, or not. Anyway, this has been published by this student from Pakistan, this student from Iraq. Yeah, you might know him, and this is from India. Now, the quality of service for dynamic RRH, and the point is, just the idea is that when you have a lot of user here in one of them, because this has a certain capacity, then you will be able to allocate some of the user to this one, and we have been able to use different techniques to be able to sort this problem. This is another publication and another work from the student where we would like to increase the capacity here using a certain technique, again with using what we call it self-organizing network. And this work has been, again, if you look here, we try to increase the throughput, the number of users, and we have been able to develop a new technique to do that, and we have been able to reduce the blocked user as well. Again, this is those students from Pakistan, Iraq, and this from India. And then we just developed a new technique for NOMA, as I said, using certain kind of polar convolutional data, and we have been able to improve this system in different ways, and we used a serial and parallel and compared between them. okay, between the two convolutional code. And if you look to this is use 6G with this kind of convolutional code. Again, this is how as I explained, when we transmit the data here, that you will see that each user will have the same bandwidth but with different kind of power. It depends on the position of the user. What we have achieved, we reduce the error rate, bit error rate, and our new techniques has been improved from 1.4 to 0.7 dB. And if you look here, we have increased the throughput as well. Again, this has been done by one of my students from Iraq, and all of them from an IEEE journal. And this is another technique which we are trying to use quantum communication and do something very new using quantum communication with the Open RAN, again to reduce two things, delay and power. Again, this student is from Iraq, the second one from Iraq, and it's obvious that we have been able to reduce the power, and here we have been able to reduce the delay. Now we are working on this again and again, and we are trying now, hopefully by another next maybe 3 to 4 months, to be able to develop new things using quantum. All those two techniques going to use quantum with the iris. Okay, thank you very much, and I am more than happy to answer only the simple question. Okay.